Hi, everyone. Welcome to our webinar, The Future of Big Data Analytics, Where is it all headed? Presented by Dr. Jim Samuel and Alex Pelaez. Before I introduce today's presenters, I'd like to go over how this webinar will work. First of all, you'll be able to view the presentation on your computer screen. You'll also be able to hear the presentation through your computer's audio system. Please feel free to ask questions by typing them in. We're going to be monitoring your questions and we'll answer your questions either in the middle or at the end of the webinar whenever they come through. Any questions that are not answered in today's webinar will be addressed after the webinar is completed. And now I'd like to introduce today's topic and speakers. Dr. Jim Samuel is an experienced global information management and analytics professional, optimization expert, researcher, and speaker. He has trained executives at global Fortune 500 corporations and has served as faculty at graduate programs across business schools for over a decade. Jim has worked with leading financial institutions and has served as a global business strategist for projects across Asia, Europe, and the Americas. Jim also consults in a CIO capacity at Axivest Financial Inc. and is an advisor to senior executives and board members of multiple companies. He is one of the key WP faculty members teaching business analytics, spreadsheet modeling, optimization, and R software at the Cotsakos College of Business's Global Business and Finance Institute. Mr. Alexander Pelaez has over 20 years of management, leadership, and strategic experience holding various senior-level technology positions with a variety of companies, large and small. Mr. Pelaez possesses a unique and diverse set of expertise, blending strategy, management, and technology, and has a successful track record of leading organizations and groups through complex issues, developing strategies for organizations, and counseling managers and executives at all levels on strategy and leadership development. For the past 15 years, he has been a professor at Hofstra University, Zarb School of Business, at both an undergraduate and graduate level in information technology. He has given numerous corporate and conference lectures on strategic thinking, management organization, and various leading-edge technologies. More recently, he is researching and advancing the use of social networking and mobile technologies to help businesses meet the needs of their customers and professionals achieve success through social media integration. Mr. Pelaez is currently walking toward his PhD and received a full fellowship to Baruch College at the City University of New York. He completed his Bachelor of Arts degree in Math and Computer Science from New York University, a Master of Science degree in Computer Science from New York University, and a Master in Business Administration in Marketing from the Zarb School of Business at Hofstra University. And now I'd like to present Jim Samuel and Alex Pelaez presenting The Future of Big Data Analytics. Where is it all headed?
Thank you, Sharon. First, I'd like to once again welcome all of you to the Future of Big Data webinar. Glad that you could join us, and I think we have a larger than expected number of participants, which is good for us all. So welcome. Big data it's a really hot topic. It is shaping the world around us, and according to the latest numbers that have just come in, we're going to see about it's going to be a $187 billion industry just in big data sales analytics alone by the year 2019. That number is going to balloon close to $1 trillion mark by 2025 when we take a look at big data analytics and the impact that it is having on the industry in the US alone. So definitely significant from a financial perspective, definitely significant from the way it's shaping competitive dynamics amongst businesses. So this is something that we all need insights into. The other part about big data analytics is that it's very fast moving. So something from 10 years ago or even 5 years ago is not going to cut it today. What we constantly need to do, the mindset that we need to have, is one of looking ahead. When we talk about big data analytics today, we need to be able to look at the past and say, how is this going to look in the years ahead? And that is what we intend to achieve with today's session. having said that, I'm going to restate one or two things about Dr. Alex Pelez. Uh, I think one or two points mentioned in the previous introduction was a bit dated. So to set this record straight, Dr. Pelez is one of the leading industry experts on big data, and he has an amazing mix of practitioner side insights and the experience that comes along with being entrenched in the industry and seeing it evolve in big data analytics, and also being on the research side, providing thought leadership. So some of Dr. Pelez's papers have been published in the top journals, and he's a highly sought after speaker. He's a highly sought after consultant. Top level executives from top corporations take his advice on analytics. So it's fortunate that we have him with us today. And with this, I'm going to pass on the controls to Alex. Alex, please take over and work your magic. Thank you.
Thank you, Jim. Thank you, everybody, for attending. Thanks for that introduction. So just a quick piece of information about this. With analytics has changed quite rapidly over the last few years, but a lot of that is also, I would like to say, media-driven, because a lot of the techniques that are available and a lot of the things that are being discussed have been around for a while. It is just recently, with certain advances and certain companies taking advantage of the information and utilizing it, that you're seeing other companies and other individuals leverage big data and analytical methods for their benefit. A few years ago, I had actually rebranded my company, focused only on analytics, and that's what you see here, 5-element analytics. And what we found is that as we started this approach, the lack of understanding inside of companies of what analytics really is a benefit to us, but it's also a teaching experience for everybody involved. And we try and demonstrate this to a lot of companies of how they can take their existing infrastructure, their existing reporting methodology and business intelligence units, and transform it into a more predictive and prescriptive type of environment. And it's something that has to occur at every level of the organization. It's not just a group of data scientists or high-end analytical people in a corner. This is something that has to occur at almost every level of the organization. So just a bit about me and the company. We're a multi-domain analytics firm. I'm also an assistant professor here at the Zarb School of Business at Hofstra University. I've worked at large companies and small companies alike in health insurance, media, as well as retail and banking. And throughout my years, I've seen the transition of companies from just working on their operational data stores and their transactional systems and bring in things into business intelligence and data warehousing. And now I'm seeing the next phase, which is using that information in a way that's very, very actionable. And so a lot of my research and a lot of the work that I do with companies is basically doing this transformational approach from the traditional reporting to, hey, can we predict what's going to happen, and when can we prescribe changes to an organization that will meet the needs of the customers and the organization as a whole. So one of the first things I like to do is I like to basically take a couple of data science definitions. So a couple of definitions that are out there is one way to consider data science is an evolutionary step in interdisciplinary fields like business analysis that incorporates computer science, modeling, statistics, analytics, and mathematics. And I thought that was a great definition from NYU as what data science is. Now, if I look at Wikipedia, it says data science is an interdisciplinary field about process and systems to extract knowledge or insights from data in various forms, either structured or unstructured, which is a continuation of some of the data analysis fields, such as statistics, data mining, predictive analytics, similar to knowledge discovery and databases. The key thing for both of these definitions is that it is obviously interdisciplinary. You're not going to have just people who are statisticians. You're not going to just have people who are computer science folks or people who are, let's say, marketing oriented who understand the data. It has to be something that integrates all of the pieces together, which means when you're trying to learn about data science and big data, you have to become acutely aware of the issues surrounding data itself, the amount of data, how to clean the data, how to structure the data. Data is not always in a nice format like an Excel spreadsheet. Sometimes it's text documents that we would get from newspaper articles, and those can be mined as well. And there are various techniques that are associated with handling different types of data. One of the other common things that we see a lot of people make a mistake with is they rely on one method to tell them the truth. And you really need to consider yourself, if you're a data scientist, as a detective. One of the best conversations that I've had with people have been in the New York City Police Department, where I learned what their techniques are in terms of being a detective. They don't rely on one thing. They rely on many different pieces of information and analysis to get the whole story together. Data science isn't that different. It needs to utilize that common knowledge of, hey, we know something's occurring in part A, in part B, in part C, but together they tell us a whole story. And that's ultimately, if you're going to do data science in your organization, or you're going to become a data scientist, that's the type of leveraging knowledge that you're going to need to take into account. You need to be open to a lot of different methods and a lot of different analysis in order to get to the final conclusion. So what is a data scientist? Well, a data scientist is one who studies data in a variety of ways to gain insight that's not previously known or understood. Now, sometimes it is previously known, and we do need to confirm things, but it's not trying to run a technique to confirm something we already know. It's running a technique to find out the answer, and if it happens to confirm what we know or counter something we know, then that's okay. But some of the bigger mistakes that we see is when data scientists try and use techniques to confirm an already preconceived notion, and this is basically a confirmatory bias, which exists in quite a number of situations. So do you need to be a PhD to be a data scientist? Well, the answer is no, you do not. We have people on our staff who are not PhDs, and they're not even master's students or master's graduate students. They basically understand data, and they understand how to do these techniques. The most critical thing that a data scientist can have are what I call I-cubed, or the 3 I's. They need to be intuitive. They have to get a good intuitive understanding of the data and say, oh, I understand that I'm dealing with marketing, or I'm dealing with customers. So I want to look at, let's say, lifetime value of a customer. Well, that deals with revenue. I want to look at the number of clicks associated with behavioral patterns on a website. Or I want to look at readmissions in a hospital. So I need to get an understanding for the healthcare domain. So a data scientist will develop an intuition for what the data is trying to tell them. They also need to be imaginative. One of the things that I see a lot of students come out with is they have some very good, strong techniques, but they don't know how to take their techniques and expand them. So a critical example, which we'll talk about later, is what happens if you do a regression and one of the variables isn't statistically significant? Do you throw it away? The answer is not necessarily. We need to understand, and we'll talk a little bit more about this p-value, but what is that p-value actually telling us? Why is that variable not showing to be statistically significant in one model, and could it be significant in another model? So you need to have some sort of imagination on how to utilize the techniques and the data associated with it. And the other one is inquisitive. You have to always be challenging the status quo. You have to challenge the internal notions of what the core beliefs are about the data. So we see this time and again where, say, a marketing department has 20 years, 15 years of experience doing, say, a customer lifetime value calculation. And then we take a look at the data and we say, well, your calculation has been good for the past 15 years, but we can actually get to a better target. So where you were 30% accurate, we're now getting to 5 and 4% accurate. And in order to do that, we have to ask some very deep questions of the data, of the techniques, but also the department. Why do you believe what you believe? What is that core value? One of the other things that we see is that some data scientists will discount that institutional knowledge, and they shouldn't do that. They need to bring that into the mix as well. And sometimes it's anecdotal, but we still need to try and figure out a way to get that into our data science methods. So these are the 3 basic qualities that data scientists really need to have, and you can kind of see how it really does form the basis of being a detective. So from a data scientist stack, when we talk about technology, what should a data scientist really have? At the very minimum, this stack, we think, actually represents the level of knowledge that is required. So the first one at the bottom is Excel. we still do a lot of stuff in Excel to do pivot tables, to do lookups, to kind of begin exploring the data. Sometimes it's a much easier tool. You know, if you've got a certain data set and you can just slice and dice it very quickly in Excel, you could do time series modeling, you can even do some basic regression, although there are some flaws with doing that. But the key is that you need a base tool that you can run to when you want to do something really quick and dirty with the data itself. The next skill up in the stack is SQL. And I can't stress enough, you have to be able to obtain data in order to do anything with data science. Learning SQL, mastering SQL, and having people who are very, very astute with SQL on your team is an absolute necessity. It is, the reason it's important is because data comes in these large volumes and amorphous type of data set. You need to be able to select the data sets that you need, not only for analysis, but when you're trying to run through some samples and just trying to get a feel for what models you could use, you need to select subsets of data that will actually work to allow you to test certain, let's say certain intuitions or certain techniques to see if it will work. You don't need to work on the full data set at the beginning. You need to work on smaller sets. The other thing is data is not always clean. So even though the transactional data or core data and operational data that gets put into some databases is what the system of record is, it's not always clean, and you need to have good SQL skills to actually pull the data out and clean the data in a format that will allow you to actually work with it well. With SQL, obviously, comes another thing where it's basically understanding how to retrieve information from a database. So other alternatives here, and I would not discount or get rid of SQL, but I would add on to it things like non-relational database manipulation, like MongoDB, or some of the other NoSQL options. Now, on top of that, it branches out a little bit. You really need to have a good statistical application that you can work with. And as an aside, a programming language. So the reason why you have both is because sometimes, let's say if you're working with SPSS, which is a popular graphical statistical application, there are certain things that you can do easier in a programming language like R or even Python for data science. Things like trying to do clean data at a level that SQL can't, or extract data from different sources that's not so easy to do in a single database. This will give you flexibility to not only get data, clean data that's not able to be done at lower levels, but also write more complex and longer types of analysis where you go from one analysis and you feed the result of, say, a logistic regression into a component for a correspondence analysis, and that may feed from another analysis that does a cluster analysis, and you bring all these things together, and that is just far easier to do in a programming language. One of the tools that we use extensively in our organization is R, because R is both a statistical application with all of the statistical models built in. We do use Python, and we do use Java as well. So we have a lot of different things that we can do. But sometimes clients will request that we do certain things in Perl or PHP, and we'll do that as well. So where do we begin? Well, at the highest level, like I said, you can never rely on one technique. So you need to become at least aware and then at least astute into all the different techniques that are available. And that's a lot. So a lot of this takes some experience. The other thing is we never start with a technique and then find the data. So what happens is some people are very comfortable with a technique and say, okay, I'm going to use social network analysis. And then I'm going to go find the data to fit that. That may not answer the question. You really need to start with what is the business or what is the client asking for in terms of their needs and their analysis of what they want. So you always really need to find that data first and let the data begin talking to you. Then you try and fit the techniques to the data. Number 3, remain unbiased at all times, even when it seems counterintuitive. And the best example that I can give for this right now is what happened during the election. If you saw all of the polls out there, people would say they would have anticipated one particular result. However, even our internal data, when we were looking at it for some other projects, one of the things that we found was that those external polls didn't seem right. So you really need to stay unbiased when you're doing any type of data analysis. Even when popular notion or something else is telling you that can't be. It's got to be this. The data is going to tell you a different story in many cases. And what I usually say is this: the data is going to tell you the truth based on what's been collected and how it's been collected. So you need to really begin to question, where did this data come from? What is the structure of the data? What is the nature of the data? And this will help you develop an unbiased approach. Avoid being bound to a single tool. If you are, make sure they're very popular tools if you have no choice, but you want to be ubiquitous in the tool sets that you have. So Python, R, SAS, because it's not the tool that makes a difference. It's your ability to look at the data, take the data, structure the data, and analyze the data in the various tools that will make the difference and give you personally a competitive advantage in the marketplace against your peers. It will also allow a company to be much more dynamic in their approaches because they don't bind themselves to just trying to do everything, say, in a SAS or an SPSS. Sometimes with companies it's a little bit different because they have standard platforms, but you can still work around that. Answers may not be what you're looking for, but they may yield different insights. The critical piece here is that you may start down a path looking for something, and you may not get what you're looking for, but you found 5 different insights that are critical to the company that can be leveraged in different ways. We have seen this a number of times where a company has asked us, can you please research, let's say, we want to know the clustering of our clients. And we do that, but as we're doing that, we find, hey, here's a different classification for your customers. And this set of customers that are very actionable in the first 15 minutes are extremely critical. We need to do something with them and keep them separate. So you never want to lose sight of the fact that there may be other things that your processes and your data will tell you that you weren't originally looking for. The other one, it sounds a little zen here, but allow the data to speak. I always joke around about this, and I usually get laughed at when I say this as well. You do need to let the data speak. You need to become one with the data. This goes hand in hand with the biasness. Your source of the truth will be the data, and you will only be as good as that data that you get. So you always want to make sure you understand where that data came from, what the structure of that data is, what the limitations of that data is, and then you begin to let the data tell you what it wants to tell you. And if you do that, you're always going to find a very insightful results. Also, avoid backfitting a model to support previous beliefs, a reaffirmation bias. You don't want to try and create a model that always proves something that you thought before. You always want to start with, okay, I've got my data, I'm going to run models, and I'm going to prove X. If X happened to be what we had affirmed, let's say a year ago, then that's fine. But you need to treat it as though it's an independent silo. You're not trying to backfit something to make sure it fits. Because you can always make something fit. That doesn't make it the best model. And a data scientist must be unbiased in that approach. So our approach here, by the way, and this is one of our key slides that we work with, is this yin-yang. And I recommend everybody kind of take this approach. There is no one thing that works. And the intuition of a company or a domain organization is no more or less important than the mathematics, which will provide information as well. And the mathematics is also no more important than the internal intuition. There is core business knowledge and experience which is essential to the insight, because they're going to kind of lead in a direction. The mathematics will provide an objective opinion or an objective viewpoint, if you will, of what is actually going on with the data. And when a data scientist takes this approach, say, I'm not going to discount the intuition of the client that I'm working with, and I'm not going to just rely on the mathematics, then what you end up with is you end up with this constant spinning cycle where you get more and more insight, stronger and stronger insight over time. So let's take a look at a topic guide of things in data science. If we have to structure data science, I'm going to create these 5 categories. It's this concept of data. We need to be able to get the data from a variety of sources, retrieve it, cleanse the data, split the data, using SQL and Excel. Technology pieces, I need to understand how I'm going to store this data. So you have the big data technologies, and then what's the most optimal way to pull the data back and forth? Should I use a relational database or a non-relational database? Do I have enough network bandwidth to actually do this? How do I get data scientists to actually get the data? What's the technology? So there's a lot of technology pieces in there as well. From a computer science standpoint, we have things like simulation and data mining, and then the use of programming languages optimally. So we find when we're doing some data analysis that when we have to basically structure our data, say for social network analysis, which is a graph theory type of analysis from mathematics and computer science, we need to write programs that are, let's say, classically written in terms of our data structures, creating lists or creating stacks and queues to create this structure appropriately. So the computer science portion cannot be discounted at all. The statistics is probably an area that people run from. You hear the word statistics and all of a sudden everybody leaves the room. These statistical methods are really important, and they're not as difficult as they're made out to be sometimes. We learn a lot of different statistical methods, in terms of regression and, say, logistic regression and ANOVA, but there are a number of techniques out there that data scientists do need to become acutely aware of. They don't need to prove the mathematics. They need to learn it like a tool. I don't need to know how a drill is built in order to use it effectively. And that's the analogy that I use. I think a lot of times in statistics, some courses are done in a way that are trying to prove various equations and formulas. They're not really needed. Not for, let's say, organizational data sciences. If you're going to become a statistics professor, obviously you need to know that. But not if we're going to be utilizing, let's say, the drill. I just need to know how to use the drill effectively. Even within statistics, there's this dichotomy of different, let's say, camps. You have frequentist methods, which are your traditional methods of, I start with my hypothesis, and then I get the data, and then I get my parameters, and then I try and prove the hypothesis. Versus Bayesian models, which are basically probabilistic models. So you'll see a lot of Bayesian stuff in A/B testing and in a couple of other areas that basically uses a priori knowledge to formulate its opinions. We'll talk a little bit about that. And then exploratory analysis is one that also can't be discounted. It is basically taking the data and running a method and allowing the data to split itself apart using this method. So you'll see things like a cluster analysis or support vector machines that will allow you to explore what the data looks like in its various components. And I don't want to lose sight of the analysis piece, because we get a lot of, let's say, data scientists who provide this wonderful model and mathematical model, but nobody can explain it to the business. And if that's the case, it's useless, because I'm not going to be utilizing that great knowledge. So you have to develop meaningful insight. You have to develop a model of how an internal company will research the data. And you can't discount the visualization, because the visualization is what ultimately makes the case. It's when you're presenting to CEOs or C-level executives or higher-level managers, and you can visualize everything that's going on, and they can see the chart, how a model mirrors actual, let's say, actual purchases, or they can see how customers separate in various clusters, so things can become more intuitive. So we don't want to lose sight of that as well. All of these are part of this yin-yang of the intuition and the mathematics. So when we talk about data, it's obviously the most important part of data scientists, because without it, you can't do anything. So we have to ask ourselves some key questions. What is the nature of the data? So is this data that's qualitative? Is it quantitative? Is the data in a structured format or not structured format? So in other words, am I looking at text coming from, let's say, Facebook messages or Twitter messages? Or am I looking at, let's say, profitability analysis or revenue and expenses from a company? The next question is, do I have enough data for analysis? And again, this will depend on the methods you're using and what you're actually looking to tell. So for example, if I'm looking to try and see if there's a seasonal effect on my sales, I'm going to need at least 4 seasons of data, which means if you're dealing in an annual cycle, you're going to need at least 4 or more data points in order to or 4 full seasons in order to figure that out. Do I need to add third-party data? So in internal cases, we have a lot of, let's say, revenue on sale. We have a lot of data on revenue and sales and what products are being sold. But do I need to add third-party data like census data on the demographic in a particular area where a particular store is? Do I want to look at the changing demographic and see how that revenue has changed based on the demographic that's changed? So third-party data is something that's available, sometimes free, sometimes not free, but there is a lot of free data that's available. I'll give you an example of third-party data that's used. We're working with a company that has a mobile application for, let's say, in terms of one of the applications they have is a weather application. So one of the things that we would want to do is we would want to get the weather from weather forecasts from NOAA, the National Oceanic and Atmospheric Agency, and see if certain weather patterns seem to affect the use of the system, which is pretty obvious, the use of the mobile application, but does it also lead to more clicks on advertising? So the question is, do they actually use it for the tool, and can we end up getting more revenue on clicks on advertisements at the bottom of the mobile application? Is my data clean? I can just answer this for you. No. No matter how good anyone says their data is, it's never clean. There's always errors in the data. There's always errors in the collection. There's always something that just doesn't seem right. That's okay. You can account for that. So it's not a big deal unless it's extremely dirty, in which case then you have to do a lot more work. How can I retrieve the data efficiently? Well, if it's a lot of data, you need to make sure that you can get the data on a constant basis and make sure you have the right data at the right time to do the analysis. So at the very basic level, we said that a data scientist has to manipulate data using either Excel or SQL. And the first goal is to be able to manipulate the data for simple descriptive analytics. That's what you see in Excel. I can create my averages, I can create my standard deviations, I can do a lot of different things in Excel and do some good work. But as you move up this chain, the predictive analytics and prescriptive analytics, you're going to be limited with these two tools. And this is where R or programming languages or SAS or SPSS, any one of those tools, is very, very useful. It allows you to move up this chain. And you'll see different formats of this online, descriptive, predictive, prescriptive, and they have different, sub-levels and so forth. But this is kind of like the general approach. The thing with SQL, and the reason why SQL is important is because a lot of the tools that you will use, such as R or even Tableau, which is a visualization tool, or something else, they all will allow you to use SQL statements to go get the data from the database. So when you need large amounts of data, Excel's limitations, it really begins to slow down around 50,000 records or so. If you're going to pull in, and we've worked with data sets that are 20 million, 50 million, 100 million rows, and you're dealing with gigabytes of data that you need to process, you're not doing that in Excel. So you need to be able to extract the various data sets that you want when you want it for analysis. How much data do I need? Well, you can never have enough data. If you're a data scientist, you should always ask for more. It's better to have more data and not use it than not have enough data and it impact your analysis. So you don't always need to use all the data, but you always want to ask for more data because it will allow you to use other techniques to find additional insights as you move down this path. But you should always make sure you have the right data at your disposal. So in other words, if we're looking to try and identify customer behavioral patterns in a retail store, then it is absolutely essential that we have that particular data. Do we have their behavioral patterns? Can I add their behavioral patterns on the website? Do I know what their sales are, at the very least? I may not need the demographics, but it would be nice to have. And don't be afraid to split the data for learning or testing. So you may have, let's say, 100,000 rows at your disposal. You work with smaller subsets to see what methods might tell you, what direction to take with the data. I don't need to use the entire data set. The reason why you may not use the entire data set is because some of the processes will take a very long time. It could take 24, 48 hours to run a social network analysis. But if I run smaller subsets of data, I test out some basic theory that I'm looking at, I can run that in 15 or 20 minutes, look at the results, and then do it again with another subset of data, and then do it again with another subset of data. And once I start achieving, let's say, a common result, and I have an idea of where I want to go, then I can use larger subsets of data. So again, you can never have enough data. You don't always need to use all the data, but make sure you have the right data at your disposal and use it wisely. From a technology standpoint, very quickly, you should definitely understand the difference between structured and unstructured data. So structured data are those things that would be in tables or in Excel spreadsheets where you have your rows and columns. That is a structured data. But what's becoming more apparent is that we can get very rich information from unstructured data, such as YouTube video comments or even YouTube videos themselves, where we can analyze different aspects of the videos or audio. We can take text analysis from newspaper articles to find out what's going on. In fact, IBM's Watson, that's how it learns. The Watson machine learns by taking unstructured data as well as structured data and comprising this very large knowledge base, if you will, that it can actually tap into. For relational data, you obviously need to know a relational database system like MySQL, SQL Server, Oracle, any one of those, or Postgres. And for non-relational data, any type of NoSQL database, MongoDB would actually help. Now, one of the things to know is that a lot of these social network sites like Facebook and Twitter, you can actually extract data from them in a structure that's easily entered into a non-relational database like MongoDB. So Facebook actually uses JSON, which is the JavaScript Object Naming Convention, for name value pairs of data. And all of that data can be sucked into MongoDB that can then be more easily retrieved from that tool than it would be to parse it out into SQL databases. The other problem of storing data is actually resolved by something called Hadoop, which is a big data technology. Sorry, I went ahead one slide, but the Hadoop technology allows you to store large amounts of data over many different machines, and it handles where the data is located. So it is considered a big data technology, and there are a lot of sub-technologies that sit on top of that. As I mentioned before, structured data basically looks like this, where you have rows and columns of individual, in this case, first and last name and a diagnosis code. This is what JSON looks like on the right side. So it basically is name value pairs, and you may have different objects here associated with it. So you see here at the top, it says interaction. That's an object because there's an open brace there. And then we have a name value pair. Type is Facebook. Content, presidential elections. Source, Facebook for iPhone. So these things can easily get sucked into a non-relational database like MongoDB. And that's what basically deals with the unstructured data much easier. In terms of the big data technology, so let's consider this. Consider that Google has a vast amount of data available to it. There's no way you could store that information in a relational database and get retrieval times as quick as Google does. So the technologies such as Hadoop, what it does is it breaks down everything, every single page that it has, into a lot of different components. And what it does is it structures all that data across many different nodes and many different servers. So really what Hadoop is a file system. And it basically puts all these different things in files across many machines, and all of it is managed by the job tracker and name node across the entire network. So it will know exactly where to get pieces of information, because what it's doing is it's distributing the query amongst all of the machines that it has, saying, get me what you have on this. It then aggregates that information at one job tracker, which will then pull it back into the final result for the individual user. All right, so we'll get into some of the statistics in this next section from that circle that we had done. But the overlap between methods and traditional statistics and computer science causes a lot of confusion. So statistical methods are really focused on a number of key factors. The nature of the data. Is the data continuous? Is it discrete, nominal, ordinal, ranked data? What's the distribution of the data? Is it normal, exponential, or Poisson type of distribution? And what's the nature of relationship between the variables? Is there a linear correlation relationship? Is it monotonic? And so forth. We use Excel, we use R, we use SAS, SPSS, RapidMiner. Any one of these tools are really good for data scientists to use. Again, we tend to use R more than anything else. So some of the example methods that you can use, well, we can use regression to predict a continuous outcome. So I want to predict, let's say, income levels for for a group of, for a demographic. Logistic regression, I want to predict the occurrence of an event, whether a download occurred or not. I may want to compare groups using ANOVA. And then, so these three are fairly common in many statistics classes, but there are other things like non-parametric group analysis, factor analysis, which you see a lot in marketing, exploring latent variables. That's used in marketing and psychology. Multivariate techniques for multiple dependent outcomes at the same time. And other things like principal component analysis, correspondent analysis, and time series, which we don't have a lot of time to go through all of these. The piece that I wanted to get to also in statistics is the concept of the p less than 0.05. So in a lot of statistics classes, for any model to be significant, we must ensure p less than 0.05. But even the American Statistical Association said it was never intended to be a substitute for scientific reasoning, which basically means as you do more and more analysis, and if you get into these statistical models, your p-value is a guide. But what we've spoken to our clients is if the p-value is less than 0.05, it means we reject their null hypothesis. But I usually say, well, what if it was 0.06? And that analysis could have made you $1 million or $10 million. Do you really reject a variable, or do you reject a model because the p-value was less than 0.05, or would you take a chance? So it really is a basis of risk. And it's really important to understand that p-value is an estimate of the type 1 error. So if we infer this as a measure of risk, risk is different for many people. And people have different tolerances for risk. So the data scientist must take this into account when it makes a decision, or when they make a decision about whether or not to keep a variable or keep a model, whether a model is working or a model is not working. Okay, so I'm going to go through a couple of case studies, but do you have any questions before I go into some of the case studies?
Hi, this is Sharon. No one has typed in any questions yet, so if you want to continue, you can.
Okay.
Okay, but feel free, people,
okay, let me do that.
Your questions.
Okay, so we're going to take one case study first. So we had a customer who wanted to predict factors that would lead to increased chargeback. And a chargeback is basically where a customer would call Visa or MasterCard and request a refund directly for a product. And so what we did was we used a number of different techniques to actually determine whether or not this occurred. They gave us about 50 variables, 47 or so variables, to say, based on all of these variables, can you tell us who is actually the type of person, or who the actions of the person that would lead to a chargeback? Well, we used our logistic regression, and we used principal component analysis. We actually used factor analysis as well. And we were able to identify, out of those 47, using a couple of complex methods, that there was a combination of two variables that actually led to chargebacks. When we did this, and we went back to the group, they made changes, and the chargebacks reduced by 95%, saving the company almost $2 million in revenue. So they were very happy about that. And again, we took their data, we analyzed the data, and using these specific methods, we identified 2 out of the 47 when together. When those things were present together for a particular customer, it led to a majority of the chargebacks. They made the change, and it ended up impacting the bottom line of the company, which is exactly what you would like. So in another example, we have customer loyalty. So customer wanted to identify which variables or groups were causing movement in the Net Promoter Score. So Net Promoter Score is a thing in marketing that basically says, like Apple, I think, is like a 72 on the scale, positive 72, which means everybody really likes it. And it's the way the scale works is whether or not you would recommend the product or service or the company to a friend. So if you did a 9 and a 10, you were a promoter. If you were a 7 or 8, you were a passive. And if you were 6 and below, you were a detractor. So what the company wanted to know was they had an NPS score, and they gave them another questionnaire. They used that questionnaire, and they wanted to see if there was a tie between the Net Promoter Score that the person gave us and any of the 36 or 37 variables, whatever the number was. So what we did was we actually analyzed this, and from the variables that we had, we basically reduced the 30 plus variables into 6 structural components. So it really reduced down to 6 what we called aggregate variables. We classified this into 2 distinct groups. And what we were able to find was that the customers who basically gave us a 0 were in this area, in this oval. And we could identify that the horizontal axis that we created was the prime predictor of whether or not they were going to give us a particular score. That horizontal axis here basically was, of those variables that we found, it was a percentage of each one of the variables. So let's say variable 1 was 40% on the x-axis. So that we knew that that was the biggest component of this horizontal axis. And it would allow us to move those numbers so that we could actually affect a net promoter score value. What this also told us was that 5s and 6s weren't that much different. And it might be easier to move 5s and 6s into the 7 than it was going to be to move a 4, or 4 from 4 to 5. So the other thing was that we saw that 7s and 8s were different. And so what we really wanted to do was also move some of the 8s into the 9 and 10 group, because that would give us a higher net promoter score. So in another case, we had customer profiling. So in customer profiling, the customer wanted to use like 1,700 columns of data from about, let's say, I think it was 50 million rows to create a profile of what we would call platinum level customers. So create this top classification. So we used correspondence analysis and logistic regression in order to identify attributes more closely aligned with the customers. And then what we did was we took that result and we utilized logistic regression to provide additional confirmation of this. Do these variables actually mean what they were supposed to mean? So when we did this, we basically created a classification scheme of the highest level, platinum, silvers, bronze, and zeros. We applied a number of different attributes to determine what characteristics would be platinum. And then the goal was to plot across 2 dimensions this consumer products group, and then overlay locations of the platinum, silver, and bronze, and zero on a particular product. So when we did this, we basically identified individual attributes, like let's say this one here is beer and wine. Beer and wine for this product seemed to be much more closely aligned to platinum than, say, 28, which was cat supplies, or 26, which was infant care. So this particular product seemed to be more aligned with beer, wine, and deli products than anything else, as an example. And this horizontal dimension basically gave us 42% of the total explained variance. So we can use those methods to say, to pinpoint, hey, is beer and wine and deli products really associated with these platinum customers? Now, when we use the logistic regression, we notice that beer and wine and deli don't appear in the logistic regression. It doesn't mean that they're not really important. It just means that the logistic regression, which is a little bit stricter, says, I understand you see a connection, but I can't confirm one. But what we did confirm was that Pet Supplies Cat was definitely anti-platinum customers. So the 2 techniques will give us, sometimes it will agree, sometimes it will disagree, and it's up to the data scientists to begin parsing this out, saying which ones do we really want to keep and what does it actually mean. We could also do the same type of analysis across the direct marketing areas. Direct marketing area is a marketing, let's say, metric that Nielsen puts out to break out the United States into these different sections. And what we could do is we could identify that platinum customers come from, let's say, more in this area, whereas bronze and zero customers are in this area. And so it tells us where we can target our marketing efforts towards. Another one we did was we wanted to predict, another customer wanted to predict the effect of downloads on mobile, on the Apple's mobile rank store, or the mobile store rank. So what we did was, since rank is ordinal, we did treat it as continuous. Again, this is what the data scientist kind of has to understand and make some judgment calls on. But what do? We use time series and correlation because we know that there's a time effect. So when we do that, we look at product 1, product 2, product 3, and we were able to create some variables that would enable us to figure out how they can spend their marketing more effectively. And basically, our prediction, this was our prediction over like a 6-day period. So given a certain amount of data, we could predict what the next 6 days were. And what you can see here, what this basically tells you is that in the 4th, 5th, and 6th day after or for our prediction, we end up becoming very accurate. Here, because we're under, it's hard to see in here, but we're definitely under 10% here. Our line as well for our rank is going to be, again, within 5%, and our rank over here as well is going to be within 5%, 1 standard deviation. So we're pretty much accurate on what our forecast was 6 days, and it actually went about 9 days out based on the downloads of the previous 14 days. That's how accurate our model was. And what we would do is we would take a look at a chart that looks like this. And again, we used our time series, we did our forward prediction, and you can see that we were pretty much roughly within 5%. And this is done in hours. I'm sorry, this is done in days. So this is 1 day, 2 day, 3 day, 4 day, 5 day, 6 day. Then you can see by the 7th day, it starts getting a little bit crazy. But again, we were able to do that. In our A/B testing, which is testing differences on, let's say, a web page where you make a change to a website, you want to see whether that change has an effect. Many of the problems in A/B testing occur due to poor design, poor implementation, incorrect methodology, or improper interpretation of results. So what happens is that you're trying to do a controlled experiment, but you don't do a very good job of it. So what do? We have different ways to do A/B testing. So if I put, let's say, a green button on a web page, I want to see if I get more orders on that page as opposed to having a red button on that page. So there are different tests that we can use, but it's all based on the distribution of the data. So a normal distribution, we could theoretically use a t-test. If it's binomial, we could use Fisher's exact test. And if it's non-parametric, where we don't know the distribution of the data, we could use a Mann-Whitney U-test. There are other tests. I'm not by any means saying this is exactly what you do. There are other tests that you can use. In fact, some people will use Bayesian models in this case to actually do the same thing. So what's a Bayesian piece? So in a nutshell, the frequentist methods data are random samples that can be repeated. Parameters of the distributions are fixed. In Bayesian methods, data is observed as it is collected with some a priori knowledge, which means knowledge that you have beforehand of what it should be, and the data known prior is utilized, but the parameters are basically unknown. So, for example, when we say parameters are unknown, if you have a normal distribution, you know that the parameters are the mean and the standard deviation. Well, here we have no parameters, so we're not really assuming anything. And I like to account for this, and a lot of the videos online will show you Bayesian methods. It's almost like a race condition. Like if I start putting more data in one side, then that group takes the lead, and then that group comes back because the other one kind of comes closer. But at some point, there's no way for one group to reach the other group. And once you have that, you have a declared winner. That's kind of what the Bayesian methods are like, because it's based on conditional probability. As you move into the computer science realm, you've got a couple of different techniques. We've got what we call machine learning techniques, data mining, simulation, and graph theory. Machine learning techniques are used to identify patterns, supervised and unsupervised learning. So I'll show you an example of that. Data mining techniques will classify groups and uncover structures of data as well, uncover structures within the data. Simulation is a technique used to simulate future events. So you can create different types of simulations. A lot of them are used also in banking and healthcare, Monte Carlo simulations, etc. Graph theory is used to demonstrate relationship between what we call actors or individuals. So a good example of this would be like Facebook, where I'm on Facebook and I have 6 friends. So those 6 friends and myself are all actors. And there's a line that connects those people together. And then their lines connect them. And so you get into this whole concept of everybody's connected within 6 degrees of separation. But graph theory can be used in a lot of different ways and in a lot of unique ways as well. So what tools do we use for these computer science-oriented techniques? It's going to be programming. You're going to have R, you're going to have Java, you're going to have Python. You know, I should really include SAS in here because SAS is a programming language, and it does have its advantages as well. So some example methods here, again, clustering, separate data points with no prior information, which is really what we'd call an unsupervised learning technique. Decision tree, which is separation of data by decisions and probability. You have neural networks, which are complex techniques used to identify complex functions. Support vector machines, which supervise learning model for separation of groups, so I can separate 2 groups from each other. Social network analysis, which will grab actors with edges to identify cliques. So as you move things together and you have all these actors, they form their little branches, like a tree branch that has a lot of leaves, but another branch doesn't. Monte Carlo simulation are techniques with different distributions, and text mining, which are techniques specialized in extracting patterns from text. So another example on, say, like a customer scorecard, again, we want to classify customers for a different customer. And what we did was we used odds ratios, clustering, and decision trees on a number of variables, like 70 variables. So a model was developed to classify customers based on their initial set of activities. The previous effort for the client took 4 to 7 weeks. So they could identify people in different groups, who was valuable, who was not, but it would take them 4 to 7 weeks. When we walked in, we were able to do a model that did it in less than 5 days of activity, and subsequently we did it in less than 36 hours. So our analysis, by doing it in under the 5 days, it enabled us to help them develop better marketing campaigns. But what it also did was it allowed them to predict fraudulent clicks. So this is one of those cases where I said where your initial analysis was for something, but you go on a little bit of a tangent and you find some interesting insights. From this model, we were actually able to identify clicks and users that were fraudulent traffic. So we could also identify trends and characteristics of top performing and lower performing customers. So there were a lot of different uses for something like this. In the profiling case, what we did was we took another similar data set which had 1,700 variables. We used SNA to take each customer and try and profile them based on the attributes that they chose. And what we ended up doing was we ended up creating a chart that looks like this. This cluster here of these individual items, the interesting part to this was all of these guys on the outside had nothing to do with the customer because they were not connected to the customer. The customer never chose them. But what we were able to do was we were able to dissect this even further and say which are the core components in the center of this, and we would identify that customer based on this structure. When we do this with multiple customers, if all of the customers are in the same group, they should share a similar profile. And so therefore, we can use this profile to predict whether someone will be a top-level customer or not. So in search term aggregation, another thing that we did was we looked at search terms for a different client. And what we used was text mining and categorization. We wanted to cluster on categories. So once we aggregated the different categories, we would find which ones had value based on a different product type. So for example, we had in the case of categories of searches, they paid listings, 79,000, auto, 200,000. How many clicks did we get? We could identify each one of these groupings as a different cluster. So for example, email was in its own cluster, but charities, causes, dating, diet, and fitness were all in the cluster number 2. What this allows us to do is it allows us to break out those clusters and start analyzing the individual behaviors within those clusters. So clustering is a great exploratory analysis tool that will allow us to take the data, segment it out in a way that we can really dive into those groups so we can eliminate the noise from the other groups. When we do analysis, as someone has to be responsible for delivering the interpretation. The key aspects of doing this is, can you create strong visualizations? And there are different tools that do this. So you have things like ClickView and Tableau. Even Excel does some visualizations, but it's not great in that aspect. How can the results be validated? And do we develop tests for the model? Once a model is created, you're not done. What you really need to do is now test that model's predictive capability with real new incoming data. Did the model do as well as you expected it to do? If it did, great. If it didn't, we need to begin analyzing why not. How will the results be received by the end users? Technically, in some cases, the users don't like the results they get, and you need to be able to tell them in a nice way. Best way to say it. If they're resistant to change, that's where the data scientist must do a little bit of extra work to look at the data once again and explain to them why what they thought was happening isn't happening and why the new results are better. And sometimes these are baby steps. If you change an entire organization rapidly, it's very, very painful. As an example, when we were doing an analysis for a customer, they were doing things on a weekly and daily basis. After our analysis, it took about a year of different projects. Now that company is now doing things sub-day. They're doing things that are, some are still daily, some are daily, but now they're going hourly and they're even going at the minute level. So as customers are coming in, they're trying to classify and segment within the first 15 minutes of the actual activity. So it really can change an organization completely. And that's sometimes a very painful thing. And it's a challenge that data scientists have to overcome. When we talk about visualization, visualization is important because there are different ways to visualize the data. So I have an example here, which is a common one on the internet for a three-dimensional scatter plot. It is very difficult to see what this chart tells you. Not impossible, but it is difficult. And there are different theories and stuff on how you should basically present multi-dimensional data. Sometimes it's just easier to present two-dimensional data in multiple graphs. But this is a challenge for a lot of companies because, again, the person who you're giving the results to is the person who's going to have to understand that chart. And they may not understand a three-dimensional chart. They may understand a three-dimensional chart. But you have to understand who you're delivering it to in order for that visualization to be meaningful, to make your entire project useful. So some of the tools that are out there, obviously Excel, which is a classic tool for reporting and visualization. Our ggplot library is actually pretty good, but it's a little difficult to use. Tableau and ClickView are very easy to use as well. When you present the results, it should always be done in terms of the original goal. You need to restate what that original goal was so that everybody who's receiving this understands what's going on. Understand how the model was obtained without the statistical details. No one cares what p-values are. When you're giving that final result, very few people will care about that. But you do want to tell them that you used a method like logistic regression that is designed to predict a binary outcome or an ordinal rank outcome. How was the model validated, right? So we did the model, we got the model, and we were actually able to validate it. Then we also want to label any concerns or limitations. We want to say, hey, this model does this, but we're concerned about ancillary data from here, or the data was not complete, or the data was not clean. We want to make sure that gets put out in front right away so that people can make really strong decisions with it. And then clearly indicate how the models or findings can be used and what is the next direction. So you don't just stop there. You say, we believe it can be used in this area, this area, this area. And it shouldn't just be the data scientist who's saying that. It should be the department or the organization that was working with the data scientist group to actually create those results. All of this has to be tailored to the particular audience. No two presentations will ever be alike. They can't be, because your audience is different and your data is different. But even if your data was the same, your audience might be different. And even if your audience was different, they may have a different perspective of what the particular goal was. So it is always important to constantly do this iterative process back and forth. So that kind of concludes the entire cycle of this whole data analysis, data science, how we present the results, and how we put everything together. So I guess I'll open the floor to any questions.
Feel free to send any questions in. Right now we just have a bunch of comments saying great webinar and they like this stuff, but nobody has asked any specific questions. But we do have a few minutes if you have anything for Alex or for Jim, or I'm just going to let it. If you don't have any questions, you can type them in and we can, Alex, we can send them to you too, if would that be okay?
That's fine. Yep.
Okay. I know sometimes it just takes like a few seconds for someone to type, but
yeah, that's fine.
Yeah. But we just have a lot of comments saying great webinar, they like the information, so. But, well, I don't want to, keep everybody here, but I'm just going to say if you do have any, okay, here we come. How has analytics changed and how do you expect it to evolve going forward?
Well, as I said earlier, I think the biggest change has been analytics was considered, and some people still consider it more on the descriptive analytics. They produce their averages, their maximums, their sums. They look at basic trends in Excel, and that has been the predominant view of analytics. When you get into business intelligence and data warehouses, presenting the data in cubes format so that you can slice and dice the data and get those averages, that has been the traditional view of analytics. What we see the movement towards is they want to predict what's going to happen before it happens. And those are your predictive models. The other part is that to find information that is not easily obtainable from the data. So for example, when you merge 20 variables together and you find the 3 that are the most important in terms of pulling on let's say the sale or the not sale or the amount of sale that's going to occur, or the clicks or readmissions to hospitals. So what we see is that as more managers become acutely aware of what analytics can do, and they ask more detailed and empowering questions, so too will the analytics follow and provide that information in a prescriptive and predictive form.
We do have some more questions. One question would be, how would you describe the job market for data analytics?
Absolutely unbelievable. It is going to be very, very difficult for companies to keep qualified people. The challenge that companies are having is they don't know what they need in a data scientist or in a business analytics. So they put out these generic job descriptions, and they may not get what they want. Some people who hire PhD data scientists, it's not what they wanted. They got a person who is this, brilliant statistician, but can't figure out, what the business really wants. But the demand is increasing for people who can do this, and it's just getting stronger. And I would equate it to almost like in the 1990s with the .com, with everybody building a website. The only difference I see with this and that is you'll have a lot of people say they'll do analytics, but they really don't do the type of analytics that we're talking about. Those people will get weeded out a lot quicker than they would have gotten weeded out back in the 90s. You will see people who are really astute at certain techniques stand out, but it's the people who can talk the business and domain language who will be the most successful. But I don't see the data scientists or analytics job market going down anytime soon.
This person says their interest in analytics is recent. So if this person is interested in working in the field and has a social science undergrad, what would you recommend continuing with?
If you're going to get a master's degree, try and get one in either, it could be in a business analytics program, it could be in a computer science program that has a little bit of data science or analytics. Social sciences is great if some of the social science curriculums already have some of the basic, how do you run an experimental design, psychology. Some of the people that I hired were psychologists because they had some of that background. But the thing is, you have to become a perpetual student in all of these techniques. Downloading the software, making sure that you understand some of the basics. And again, I would use that stack as my guide. I would say, make sure I master Excel, make sure I know SQL. Then if I'm taking classes, then I can learn all of the techniques that have been listed here, either in a statistics. I'd be careful because sometimes statistics departments will be pure mathematical and math proofs. So if that's your cup of tea, then that works fine. But business analytics programs are usually designed for business-oriented solutions. They don't necessarily go through the proofs. Or data scientists will be in a computer science department that talk about these similar techniques.
Okay, that kind of answered the next question as to where should people without a background start to learn. So thank you. The next question is the processing of data differently today than it was, say, 10 years ago? This person believes she read on Hadoop, and the processing is different as the data is not pulled and then processed.
It depends on what you really mean by process. We definitely do things different than we do 10 years ago. Even the pulling of data is radically different than it was 10 years ago. So there is a difference. Hadoop will process things at a different location, so it'll process it at the nodes, at particular nodes, before it transfers it up to the next node to give it to you. And there are a lot of different ways that can be done. So it really depends on how that question is, but it is definitely different than it was 10 years ago.
Okay, another person going back to the career. Do you think a math student, that kind of background would suffice for data analytics?
It definitely helps. There's no question that math, computer science definitely help. And then it becomes, the person's ability to really, that person's ability to really, convey to the client that they can do this particular job.
Okay, I'm not sure if I'm going to say this right, but this person said with regards to training, what delivery methods are used? I'm not sure if that's...
In terms of training, if you're talking about training for these types of classes, you can get a lot of material on YouTube. You can get a lot of material on different universities. I think William Patterson offers a pretty good one. in terms of analytics. I know we offer one in terms of analytics as well, and they have different both online programs or in-class, programs.
Okay. All right. I think we're getting close to the end, and the questions are kind of slowing down a little, but there are a couple of people asking if the presentation will be available online. Yes, it will be on the William Patterson YouTube channel. Anyone who registered or attended today, you will see the presentation up there by this afternoon, probably within an hour, actually. Here's another question. Do you think big data will be around indefinitely, or the next big thing will come soon and replace it?
Big data will be around for a while, and then that's like the computer came around, and then the PC, the mainframe, and then the PCs, and then we went to web browsers. It's always going to evolve. But even from that stuff, the core stuff hasn't really changed. A lot of the techniques that we're talking about now for predictive analytics have been around for 50 years. We're just using them in a different way. So it's really going to come down to the imagination, the intuition, and the initiative of the individuals who are utilizing this technique, and that will transform everything as we continue on. So it's always transformational. It's always moving, but it's going to be there for a very long time.
Okay. Jim, if you have anything further to add?
I think Alex has been answering those questions spot on. I just got unmuted, so thank you. And I would probably like to ask a question, in fact, Alex, just your comments on how technologies such as machine learning, deep learning, and even emerging artificial intelligence technologies will have an impact on jobs. You already mentioned that it's a moving target. So how do you see these emerging technologies replacing old jobs and creating new ones?
I don't think there is any question that this type of stuff will, machine learning, deep learning, are going to change the way companies behave and way they do business. That will inevitably trickle down to the jobs that are there. A good example will be, first of all, there are two examples. Amazon is doing a lot of analytics to try and figure out what you're going to buy before you buy it, so they can have it in the warehouse closest to you at the time you buy it. And it's really sick the way the way they're doing that. I mean, it is amazing that they can get to that level. But you could also see things like the automation. The data is going to lead to easier capabilities for automation. That automation could lead to displacement of jobs. What's really important, and this holds for everything, and this has been, I think, the case, and I've advocated this for decades, people have to continually learn. And jobs are going to move from one thing to the other. And as we do that, if we become complacent in any particular job we have, we increase the probability of it being removed, of us being removed, or it being removed from us, one of the two. The thing about data and this analytic stuff is it's intellectual knowledge. The intellectual knowledge is something that is a lot more difficult to outsource to someone else unless they have that same knowledge. And one of the things that we see, like as an aside, is companies are coming to us because we're closer to where they are, as opposed to just outsourcing it even overseas. They can get someone to do the data science portion, but then they don't have a way to really interpret it. This is not something itself that is a commodity, but I can see how data science and techniques will create efficiencies within the organization, which could lead to displacement in various parts of the organization. And that includes things like marketing. Because if I get better at figuring out what a customer is going to want before they want it, I may not need as much creative talent in that sense, because I can have the machine automatically do that to a particular customer. So not a very straightforward answer, but hopefully I answered, at least I gave it in the right direction.
Yes, absolutely.
I'm sorry. If it's all right, we have one more question. How do you see blockchain technology affecting big data analysis in the future?
You know what? It will have an effect in the future. The question is really when and by how much. And I think what's going to happen is there's a lot of different changes that are going to occur to see how that's going to ultimately have an effect on, on what we're doing here. There are a lot of incremental benefits that are going to occur you know, in different areas, and you're going to see everything spread out like a tree. So it's hard to really, you know, give a definitive answer to that particular piece, but that's probably the best I can do at that point with that, because it's not a very clear. I wouldn't have a clear opinion on it just because of the way the nature of the industry is.
Okay, thank you.
Just to add what Alex is just to add to what Alex has already said on the blockchain bit. See, I think it opens up a new dimension for analytics, because what happens with the blockchain is that you're storing information and tagging information in an entirely new way. So when we speak about analytics, ultimately it's information. So blockchain opens up a new avenue for analytics. I think as far as the industry is concerned, especially the financial services, they're taking a very serious look at adopting blockchain technologies. Now, no technology is perfect, but what we have seen so far with the blockchain technology is that it serves as, in an oversimplified, using oversimplified language, it serves as a unique identifier that can be tagged to data. So what could, this is my conjecture, what could happen in the future with blockchain technology is that we could see a move away from the traditional concept of structured data, and we could also see a move away from the traditional concept, if I may use the word traditional with unstructured, a move away from the traditional concept of unstructured data, and we will see a greater acceptance of organic structures of data, because blockchain technology will enable that. Blockchain technology will enable all kinds of data to be used by all kinds of industries confidently till weaknesses are identified with the blockchain concept of it providing unique identifiers.
Okay. Well, thank you very much. It's actually 10:47, so if you have anything else you want to leave anyone with, otherwise, once again, I'm just going to repeat that the video will be up on the YouTube channel. If you've registered or if you have attended today's webinar, you'll be emailed the link and this presentation. I want to thank Jim and I want to thank Alex for doing this presentation. It's very interesting. Thank you again. Thank you for attending. Anything else? No?
That's it.
Okay, well, thank you, everybody.
Thank
And
you so much.
we hope we'll see you at another webinar. Thank you very much for attending. Bye.